Alright, hey guys. This round, today there was round 712 by the one and only One Gone. It's a pretty cool round. I actually did a screencast for it this time. So I'm not going to attach it to this video for the sake of like having solutions be brief, but the basic idea is that I'm going to unlist it because it's not very exciting. It doesn't have that much commentary. I didn't turn my face cam on because I wanted to focus a lot, and it didn't really make that much of a difference anyway. But um, yeah, so basically, I'm just going to go over the solutions like I usually do for at the very least all the div 2 problems, because I have solved everything that corresponds to div 2 problems, and that's basically going to be it. Yeah, so in the description I'll paste the link to this unlisted screencast if you happen to want to watch it for some reason. But this is of course going to be public because you can see it right now. So we go over the div 2 problems and also the div 1 perspective. So this contest went pretty okay for me because I solved a good amount of problems, but the problem was penalty. I did some dumb things on A, and then did a dumb on C, and then did also a dumb on D. So that wasn't fun. But I mean, what can you do? The solution is to not make mistakes, which is how do you even do that, you know? So just, I don't know, try and improve things more. I'm not really sure. Anyway, so this is A. You hate palindromes because they give you deja vu, and that's is that the only time this theme is ever mentioned in the contest? I guess that's one criticism I have. Does it ever show up anywhere else? Does it show up in F? Is there deja vu in F? There's also oh, that's funny. They have flip and then balance. That's cool. That's kind of funny. Okay, anyway. What we're going to do is just go over this. So this is div 2A. Doesn't correspond to 1 in div 1. Basically, we have a string. And we're going to insert the letter A exactly once in it, in exactly one position. We want to make it so it's not a palindrome. Okay, so first of all, when can we do this? If the string is all A's, then we can't, because there's no place we can put an A. The string is still going to have all A's when we put an A in it, and that means it's a palindrome. And otherwise, there's always an answer. And because we have to construct the answer, let me show you how we can do that. So if the string is odd length, then because it's not all A's, there's some character that isn't A. So if we consider the odd number of positions, we're going to find the character that isn't A. Say it's either second from the right or fourth from the left, which means that we have to put it so it's going to be at the opposite position. Meaning that suppose it's on the left side of the string. Suppose the non-A character is on the left side of the string. Then we're going to put it here so that it pushes these characters to the side, and then it matches with this character. So we'll have some character that isn't A that matches with some character that is A, and thus it's not a palindrome. For even length, it's going to be a similar idea. Basically, we find any character that isn't A, suppose it's here. Then we're going to put it in the place so that it matches with that character. So we can think of it like having blank spaces. And then if it's on the right, we're going to put it at the third blank space from the left, which is before this character. And if it's on the left, then we're going to put it at the third blank space from the right. I guess that's a way to think about it. But anyway, for odd and even, you can always do it. Okay. Refresh. Yeah. Again, I don't want to look at my place because it's probably not great. Or it's going to be some sort of rating loss at least. Just because of my penalty. So this is div 2b. It doesn't correspond to any A. Or a div 1 problem. There's a binary string. And in one operation, you can select any prefix with an equal number of 0 and 1 symbols. So all symbols in the prefix are inverted. So First thing to notice is that because we have to have an equal number of 1s and 0s, we have to have an even length prefix. But it turns out that doesn't matter much. What really matters is the observation that when we flip a prefix, like, what does it do to the rest of the prefixes? Right? So suppose we have some string A, I'm just going to not even like use examples, and some string B. Now suppose we have some prefix that's flippable. Put it here. That is, there's an equal number of 0s and 1s here. Then when we flip it, every 0 is going to become a 1, and every 1 is going to become a 0. So basically we swap the number of 0s and 1s. But they're already equal, so they're going to stay equal, right? So really, like, when we do a flip, it doesn't change the number of 0s and 1s on the prefix at all. And for any prefix that's like a sub-prefix of this, when we flip it, it's going to flip the entirety of that prefix as well, meaning that it's going to change the 0s and 1s to the same thing. I mean, like, they'll stay the same. And for any prefix that contains this prefix, it's still going to be the same thing, because every 0 and 1 outside of it is unaffected, and everything inside is going to be like bijected, sort of. Every 0 will become a 1, every 1 will become a 0. They already were the same number, so they'll stay the same number. So with that in mind, basically our operations are independent. So consider now every prefix that's possible to be flipped. So we can basically just iterate through the string and then place like a marker at every point where we can flip it. So for example, all of these prefixes can be flipped, and this prefix and this last part cannot be. So basically now we have these sort of like ranges, and we want to make all these ranges equal. So we can't flip like something in this range and then not flip something else in this range. That is, like, everything in this range together must be either flipped or not flipped. So the state of like everything in the range where the state is either flipped or not flipped is the same. But every range other than that is independent, because we can flip exactly this range by flipping this prefix, which flips this whole thing, and then we flip this prefix, which flips everything else, meaning that everything here will be flipped twice, meaning that it doesn't change, and everything after will be flipped 0 times, and everything in between will be flipped once. So it's like prefix sums, basically. So basically we can flip any range independent of the other ranges, and we potentially can't flip the last range. Yeah, it's not guaranteed that. So yeah, basically what that means is, now if we consider these ranges in B the same ranges, the last range in A must be exactly equal to the last range in B. That is, the range that can't be flipped. If that doesn't exist, then we're good. And so if that's not possible, then there's no way we can ever make A equal to B. And similarly, all of these ranges independently must be either equal to the corresponding range, or like we can flip it to make it equal. So these ranges must be like, sort of like, yeah, like either they're exactly equal already, or they can be flipped so that they're equal. So to find the ranges, again, we just look at all the prefixes that have an equal number, and then we check that. And then for the final range, we can't flip it, so they have to be exactly equal. And this final range may also not exist. Yeah. So a simple way to check that is to just say, like, for every value in the range is like, if this is not equal to this, then the first character must also be not equal to it. Or like if it's equal, then the first pair of characters must also be equal. Implementation wise, that's sort of how it can go. I don't have code for it, so I'm sorry for that. Anyway, so this is div 1A or div 2C. Or yeah, 2C. It was a fun problem. I got 3 wrong answers, which is totally awesome. So that happened, and yeah, so basically that's how this went. This single problem basically decided my entire contest. It gave me such a bad penalty because it was like over 10 minutes of penalty and 3 wrong answers, which is minus 150 points. And it was so bad that when I was looking at the standings, like I had the second worst penalty of anyone who solved 4 problems, which is insanely stupid. So that's how that goes. But anyway, this is how, just checking and making sure, always a simple sanity check. Yep, so this is how that's gonna be. So basically the way this problem works is you have a string of length n, a binary string. And basically what you need to do is you're going to create two bracket sequences. If you don't know what a bracket sequence is, you should read the statement. But basically, a way to represent bracket sequences is like it's balanced if and only if, like if we convert all of the left-facing parentheses or the right-facing parentheses to 1, like the left parens or whatever, and then we change the left-facing parentheses to -1, then every prefix sum must be greater than or equal to 0, and the whole sum must be exactly equal to 0, meaning we have as many lefts as rights, they're equal, and for every prefix we have at least as many lefts as rights, because otherwise it means that like there's some right, there's some -1 that doesn't have a match, because everything to the left and to the right is already matched with some other one, meaning that like that one doesn't have a match. So yeah, so what are the conditions for like it? So we have to create two different bracket sequences, and or not necessarily different. We have to create two bracket sequences such that like if this character is 1, then these two characters are equal, like this is equal to this, and if this character is 0, then this is not equal to this. So like this means equality, this means inequality. Yeah, I guess. Yeah, I guess, is that the right word? Sure. Basically we need to see if it's possible. So first of all, so what this means is that every 1 is going to mean that either we have 2 right parens or we have 2 left parens. Left facing or right facing. I'm going to use that for left and right. So this is a right paren, this is a left paren. Actually, it doesn't matter that much. Like right facing paren, left facing paren. Basically, like for every 1, we're going to have an even number of left facing parens and right facing parens. And for every 0, we're going to have exactly 1 right facing paren and 1 left facing paren, no matter how we do it, because like they have to be not equal. So really what that means is like, because both of the prefix sums must be 0, that means also n is even. So that means that we must have n over 2 left facing paren and right facing parens in both of them. So if we have an odd number of zeros, then that means that like the number of left facing parens we have in this string is going to be not equal to the number of right facing parens we have in this string, or left facing in that string, because their parities are going to be different. So that means they can't be equal, so it's not going to be possible if you have an odd number of zeros. Another thing we have to deal with is that both of the ending characters must be 0. Yeah, both of the ending characters must be 0, because like otherwise, if this is, or both of the ending characters must be 1, because if this is a 0, for example, then like at least one of the characters must face towards the end, meaning that it like can't be matched with anything. So that's not possible. And similarly for the other end, one of the characters must face towards the left end of the string, meaning that it can't be matched with anything, meaning that it's not possible. And in every other case, it turns out that it's possible. So we have an even number of zeros, which means because n is even, we have an even number of 1s. And so, why is that important? Because it means that like we can pick like the first half of the 1s and have them all face to the right. And then we can pick the second half of the 1s and have them all face to the left. And note that this bracket sequence by itself will be balanced because we have the same number of left facing ones as we do right facing ones. So we've sort of handled the 1s. Now we just have to handle the zeros. And the way we handle the zeros is we simply alternate them. So for example, say we have like a 1 and then a lot of zeros and then a 1. So basically we can make this that, we can make this that, and then for every 0 we just alternate them. So we say the first 0 is going to have left facing or right facing and then left facing. And the other 0 is going to be the opposite. And then this 0 is going to be that, and then opposite, and then opposite, and then opposite. And the reason this works is because for every 2 zeros, their prefix sums will always balance out to 0. Like maybe we have a -1 here and a +1 here, and maybe we have a +1 here and a -1 here, but it's going to balance out to 0 for every 2 characters. And this is nice because because we have to have a right-facing print at the beginning, and we have to have a left-facing print at the end. It means that we're going to sort of like we're gonna move it over. No, what does it mean? It means that no matter what, we always have like a prefix sum of at least 1 from the start. And it means that at every point, despite the zeros, we're always going to have a prefix sum of at least 0, because this will only affect the prefix sum by at most -1, or it could even like increase it by 1. But the point is it won't decrease it by more than 1 at any point, meaning that because we automatically have more than 1 at every point from this, then we're automatically going to have more than 0 at every point, because the zeros can only cancel out like at most 1. So that's the way we can construct it. We simply alternate the zeros, and then it always creates a balanced string. Yeah, makes sense, I guess. Okay, so this was fun. This was called 3 coloring. Okay. It's interactive. You have a n by n grid. On this grid, this contest could have gone so much differently. I just want to like comment this. Like this contest could have gone so much differently. I could have solved A in 15 minutes and then B in 8 minutes. So that would give me like 23 minutes. And then maybe C in like another like 25 minutes, because this again was a very stupid mistake. So that would give me like 50 minutes on A, B, and C. That would be awesome. With like no penalties, right? And then maybe like an hour on D or something. Actually, how long did this take? No, it was 40 minutes on D. So that would be an hour and 30 minutes in. I would have time to read E. I'd have like very few penalties. It would be so good. I would have been doing so good. But no. Unfortunately, no. That's how it goes. Okay, so here's how this works. You have a grid. Now you're playing against Alice and you're Bob. Because like, I don't know, Alice and Bob. So Alice is going to give you a number between 1 and 3. So say this number is like X. Then what you as Bob has to do is you have to pick some Y such that Y is not equal to X and put it on the board in some location that doesn't already have a number on it. And after everything is done, what you need to do is you need to make it so that no 2 adjacent cells, either horizontally or vertically, have the same number. So what sort of strategies can we do for that? So imagine like a chessboard. This is just like the way to think about this is just to like have it occur in the past. So that sort of fits the deja vu theme actually. Like if you've seen a problem that sort of like requires like no 2 adjacent cells are equal, a good way to do it is often to use a chessboard thing. We're going to like imagine a chessboard, right? So like every cell where the row plus the column is even is going to be like black, for example, or orange in this case. And then use some color that stands out. And then every color where R plus C is odd is going to be purple. And then we're going to make sure that no orange number is ever equal to a purple number. And what that means is that Did I miss any? That was dumb. What that means is that, like, because no orange is equal to purple, no number will ever be equal to an adjacent one, because every orange is only adjacent to purples and every purple is only adjacent to oranges. There's no orange that's adjacent to an orange and no purple that's adjacent to a purple. So that's the chessboard idea. So really, like, how are we going to make that happen? Well, imagine we already filled out all the orange ones. Imagine like these were all 1, for example. Imagine like we can make it so all the orange ones are the same. Then no matter what Alice gives us, if Alice gives us a 1, we can put down a 2 in all these locations. Or like, if Alice keeps giving us 1s, we can put down 2s. If Alice gives us a 2, we can put down a 3. And if Alice then gives us a 3 to try and screw us over, we can put down a 2. So no matter what, we can put down at least one of 2 and 3 to make it so this chessboard will work. But that's only true if we've already done if we've already made the oranges work out. So now we've reduced the problem to saying, can we make it so we always have one of the? Can we make it so we fill out one of the colors, either orange or purple, such that every orange color is the same or every purple color is the same? So we know orange and purple have to have different numbers. So let's assume we're going to assign 1s to the oranges and assume we're going to assign 2s to the purples. Note that at any point, no matter what Alice gives us, we can always do at least one of these, right? So if Alice gives us a 1, then we're going to start filling in the 2s for the purple. And then if Alice then gives us a 2, then we're going to fill in one of the 1s. And then no matter what Alice gives us, we can always continue our progress of filling in these values until we finish off one of the colors. Then once we do, we can apply the other strategy. So now, because we have all the 1s that are filled, we have 2 remaining numbers, basically anything that's not equal to 1. So that whatever Alice gives us, we can take one of the numbers that isn't used and we can put that on the other side of the... we can put that in all the purple cells. And if we happen to finish purple first, then orange will become either 1 or 3, because we know we use 2 for purples. And then that means that no matter what Alice gives us, we just use a number that she didn't give us. And then that's what we can put down. That's a horrible 3, I'm sorry. I'm very sorry for that. But yeah, and then that way we can always win. Maybe people will fail system tests. I don't know. There's like a very slight hope. Look at how bad I was doing though. Like 700 people have solved this by then. It was not a good time. And I solved B pretty quickly. But yeah, it was just not good. Ended up saving it though by solving D. That was what saved me. Okay, so this is 2E. Wait, I didn't even do that. Okay. Well, this is div 1C or div 2E. You have to solve a traveling salesman on a very special graph, where basically you have a line of nodes. Each value has 2 values associated with it. A value, I'm going to color this red for a very specific reason, a value A and a value C. And so every value A, for example, say we have 6, so we have, I'm going to sort them by A because that's something that ends up being important. So we have 0, we have 2, 3, 4, 7, and 8. And then in the value C, we have 1, 3, 0, 2, 1, 4. We start at the cell that's numbered 1, which in this case would be this one. So this has the number 1. What we're going to do is we're going to go in a path that visits every cell exactly once. It's horribly ugly. And then we're going to return to 1 at the end of it. We want to do it at the minimum cost. So the cost of making a jump is the maximum of the cost at I. So it's the maximum of Ci, like this cost value, and the difference between the A value of the value we jump to and the A value of the value we jump from. So I'm going to uncircle those because that's... AJ minus AI. Cool. So what? Note that like if this max wasn't here, then the cost would be fixed, which is kind of nice because every AJ will be used exactly once, every AI will be used exactly once, and every CI will be used exactly once. So in fact, the cost would just be the sum of the CIs, which is interesting. But that's not relevant. We're solving for a maximum. Actually, maybe that could be like an easier version of the problem, but like at the same time, it's not that interesting. Oh, it might be. I don't know. So basically, yeah. So what we're gonna do is we need to figure out the path with minimum cost that does this. So we're gonna mess with this formula a bit. Note that no matter what we do, we're going to have to pay at least the costs every time. The answer is going to be at least the sum of the costs. So like, if we sort of like, we know we're already going to pay at least the sum of the costs, we can sort of do that beforehand. So what we can do is we can drag the CI out. We can subtract CI from both of these and then add CI at the end. So then we end up with CI plus the maximum of 0 and AJ minus AI minus CI. If we mess with that a bit more, we can say that CI plus maximum of 0 and AJ minus AI plus CI. So we can sort of handle this by saying at the beginning or at the end, we sum up all of the CIs and add that to the answer. So really we can ignore this. We're trying to minimize the sum of this quantity over the jumps we do. Now, a way to formulate this problem is to, just like a way of thinking about it, is to say we're going to assign every node a direction. Or we're going to assign every node like a place we're going to go to. So 1's going to go to some place. 2's going to go to some place. I don't know the actual ordering, but like the point is every node is going to go to some other node. I don't think that works. Oh yeah, it does. Okay. And we have to do it in such a way that we form like a cycle, right? So we're basically like assigning the values of permutation so that the permutation is one big cycle and like everything will work. Right, so how's this going to work? Note that with this representation, if we sort by AI, then every jump that goes to the right is going to be free. Or it's going to cost 0. Because AJ minus AI plus CI is like, because we're subtracting out CI here, like AJ minus AI is greater than or equal to AJ minus AI minus CI. So the actual cost is less than or equal to the difference between the AI values. So if we sort by AI, any jump to the right or any jump from a larger A value to a smaller or equal A value is going to be free. Because this is an upper bound on the cost and it's already 0. Right? So it just has to be 0. So what does that mean? Actually, I'm not sure why this works. Wait, does this work? Am I going to fail system tests? I don't know. Am I going to fail system tests? That is a question. Because I think I sort of ignored one in the process. Actually, wait, no. Never mind. It's okay. It doesn't matter. Right. Okay. So that's fine. So every jump to the right is free, right? So like we can just ignore those. Cool. So now let's redraw it, except we're only considering the jumps to the... What did I do? Okay, I'm just gonna like copy this over and then erase some of the mess that I just made. Yeah. I'm gonna say this exists, this exists, this exists, and this exists. Okay. Now we're going to jump over from... Now we're going to only consider the jumps that go forward. Right, so for example, say we do something like that, and then something like that, and then something like that. Does that work? It should, right? It does work, right? Yeah. Okay. Now the basic idea with this is like, we have to include the node with the lowest value of AI. We have to include the node with the highest value of AI. And that means that for every other node, like color it like orange or something if we visit it. So say we make like this path. No, wait. We know that at some point we're going to have to get to here. That means that like when we get to here, basically every node that isn't orange, we can get there for free. Because we can jump backwards and have all these costs be free. We can jump to lower AI values. So basically we can arrange it so that this cycle sort of like goes from the largest node to the smallest node, and then from the smallest node to the largest node. Note that it will form a cycle, which is equivalent to starting from 1 and ending at 1. Meaning that we don't really care about 1 anymore. As long as we have a cycle, we're good. So note that also because every backwards jump is free, there's not going to be any sort of like interleaved structure. Like for example, say we have something like this, where we have this, which goes to this, this will go to this, and then this separately will go to this. But like if we're jumping from here to here anyway, and then we're going to jump from here to here, and then maybe do some stuff back here, we might as well like not make this jump, because we already have like enough power to make that jump. Alright, so why do that anyway? Yeah, so we can basically get rid of that. So we assume now that we're picking some sequence of nodes, starting at the node with the lowest AI, and then visiting in order of AI the nodes that we're going to. Like in visiting in order of the values of AI, the additional nodes. Then we want to minimize the cost. So now the idea is, now that's where this sort of like, we mess with the formula a bit. This is where this becomes important. Now we consider the value AI plus CI. For example, this would be 1, this would be 5, this would be 3, this would be 6, this would be 8, and this would be 12. The idea now is that we want to, the nodes we're going to paint orange are going to be the nodes that are local maximums. of AI plus CI. Meaning this value of AI plus CI is larger than or equal to anything before it. Now that's cool. And yeah, so like without proof, that's what the solution is. We're going to consider only the local maximums. Without proof, hoping I don't fail system tests, which I don't know about yet. But without proof, that's what this is going to be. So yeah, basically that's the order we go in. So we find all the local maximums, stick them into like a list, and then go through that list and figure out the cost of each of these consecutive jumps, which is easy. We know the cost formula. Like we just plug them into the formula and sum them up. And then we add the sum of CI to that, and that's our answer. So the reason we only care about local maximums is like, suppose we have something that isn't a local maximum, then, for example, like suppose we included this 3. But like, why would we do that is the question. Because we can get this 3 for free. And that means that whatever jump we make to the thing that's after 3, if we jumped from 3 to 6 instead of 5 to 6, then it means that somehow we have to like jump from 5 to 3 as well. And so that's sort of an extra cost, like we're using the 5 and then we're using the 3. But we can have this jump be for free. Well, if we jump from the larger one to that. And note that this cost is going to be higher than this cost. Or this cost is going to be strictly higher than this cost. Because we know that, or like at least as high, because we know that this value AJ is going to be higher than that. So what that means is that this value AI plus CI is going to be lower here than it is here, meaning that we subtract out a smaller value, meaning that we get a larger value, meaning that our cost could be higher. So really like this cost is higher than this one, and we can already do this one, so why not do this one instead? Because we don't have to account for this edge. We can get this node for free by jumping backwards. So that's the idea. And now the other idea is that now we need to show that we're always going to use all of the local maximums. And the reason we do is I think we can do out some formula bashing there as well. Hopefully I don't fail system tests. We should be able to do some formula bashing where we for example, we have some nodes here. Assume these are all local maximums. So say we have 3 nodes. And we want to show that it's never going to be better to take the longer jump than to take the 2 intermediate jumps. So let this have AI, and then let BI for like brevity. Actually, no. So this has AI, or this has A1, this has A1 plus C1, this has A2, this has A2 plus C2, this has A3, this has A3 plus C3. So right, what's the cost of taking the upper one? The upper one is the maximum of 0 and A3 minus A1 minus C1. We also note that because these are local maximums, we have all these inequalities, that these are less than or equal to each other. And if we take both jumps, then we get the maximum of 0 and A3 minus A2 minus C2, plus the maximum of 0 and A2 minus A1 minus C1. Now we know that this value is going to be larger than this value. So if we sum these up, how would this work? Yeah, so automatically, like, this cost is less than or equal to this cost, because we know A2 plus C2 is going to be larger than A1 plus C1. So really we just need to show that taking this cost isn't like that bad. Okay, we do pass, good. So we just need to show that this taking this cost isn't going to be that bad. And let's see, how would you do this? I might split this up in the timestamps. Yeah, the way you would do this would be to let's see, A2 minus A1 minus C1. Oh, yeah, of course. A3 is larger than A2, or greater than or equal to, meaning that this cost is also going to be less than or equal to this. The question is, like, because we're summing them, is that better? So, like, specifically the difference between these costs is going to be, so suppose this is 0, then like automatically the other ones are 0 because they're always less than or equal to this. So we, well, like, if it's not 0, then that's sort of what we're interested in. So like basically the difference between this cost and this one is A2 plus C2 minus, all right, like this should be a negative difference. So it's that minus that. That's the difference between these two. And then this is A2 minus A3. It's like, what if these are all equal? How does this work? It's like if this is non-zero, then the idea is that splitting up these costs should be not that detrimental. Also note that if we like add these two up, we get like A3 minus C2 minus A1 plus C1. I mean that if both these costs are greater than 0, if both these costs are greater than or equal to 0, or like greater than 0 strictly, then the sum of them is going to have an extra C2 subtracted from it. Meaning that like it's going to be better. I don't know, it's kind of a shaky proof. But proof by like it probably works, and also like proof by like this has a larger cost. Like this has a larger like thing being subtracted than this one. So we want to like do as much of a jump from possible as possible from that. I don't know. Honestly, I don't have the greatest proof, but I guess you can mess with this formula and do out some casework for like equal 0, less than 0, greater than 0, and I think it should work out. Most of the things do work out from what I've gathered. Like again, if this is equal 0, it automatically works. Otherwise, if this is greater than 0, like the sum of the costs is different by C2. Oh yeah, okay. Actually, yeah, that's how that works. So if any of these are 0, again, because both of these are individually less than or equal to this, if any of these are 0, then it's going to work. And if not, then both of them are greater than 0, meaning the maximum doesn't affect them at all, meaning the cost is the sum of these things, and this by default is equal to this, which is less than that because C2 is positive. So then it works out. Yeah, okay, cool. So that's how you'd prove that. Basically, the cost is always going to be lower to do this jump and this jump rather than this jump alone, solely because of these inequalities. Okay, so that handles that. Now we have one problem left, and this is div 1D, which had a lot of pretests. Could have had multitest for this too, but I guess it doesn't matter that much. Out of respect, I guess he didn't have multitests. So this is 1D slash 2F. And what's going to happen with this? So essentially you have some cards. Each card is a pair of numbers. Actually it might be easier to write it like this. So 3, 10, 6, 4, 1, 9, 5, 8, and 2, 7. So the idea is you can flip some of these cards. So you can change the order of them. So like I can put this on the top and that on the bottom. Then what? Then what we're going to do is we're going to say, what the hell is that? Let's throw that away. Just found something on the floor. We're going to say that like once we do our flips, what we need to do is we need to order the cards in any way we want, in such a way that the top values, I guess, or how does it work? Yeah, the top values or the left values in the input are sorted in, sorted in normal order, so in increasing order. All the values are also distinct, by the way. So these must be sorted in increasing order, meaning we put the 2 first, then the 5, then the 6, then the 9, then the 10. And the remaining values, the bottom values, must be sorted in decreasing order. So they must be reverse sorted, meaning that we have that, and then that, and then that. So this works. And note that this is the only ordering that will sort the top values, meaning that like we have to do it that way. But the bottom values don't work, because they're not sorted in decreasing order. So that doesn't work. But something we can do is something I'm going to read the sample explanation for because I don't remember how to do this. And we flip 1, 9, and 2, 7. So that's how that works. 9, 1, 7, 2. Then we order these numbers by this. So we have 3, 5, 6, 7, 9. And on the bottom, we have 10, 8, 4, 2, 1. And so it works. This is sorted, this is reverse sorted. So it's perfect. The question is, if it's possible, so is it impossible if so print -1. Otherwise, print the minimum number of flips it takes so that we can do the reordering. The reordering has no cost. It's simply the flips. So, okay. Now, one idea we can have is that suppose suppose we have a solution, right? So suppose we flip these. Then we sort them in increasing order. Then note that actually I'm gonna undo that. Note that because this is sorted in increasing order and it solves the problem, this is sorting in decreasing order. Meaning, if we reverse this whole thing and then flip everything, then we have another solution. We can reverse the order of the cards and we flip everything. So that now this is sorted in decreasing order and it's on the bottom, and this is sorted in increasing order and it's on the top. What? So what that means is we can do something like 9, 7, 6, 5, and 3. So we flip everything and reverse it. Reverse everything. And that way, suppose this used X flips, then this answer could use m minus x flips, because everything we flipped to make this work, we can instead not flip that and flip everything we didn't flip. So it's sort of like taking the complement of the flips. So for any answer, we could also, for example, take the minimum of that answer and m minus that answer. Cool. But don't get hung on that, because that's where my wrong answer came from. Cool, we got accepted. 2 sat, interesting. All right, so basically the idea is, look at 1. Look at where the 1 is, right? The 1, either we put it on the top, in which case it has to be at the beginning, because the 1 is less than everything else, meaning that it has to be at the beginning if it's going to be sorted in reverse order. Or we put it on the bottom, meaning that it has to be at the end. So because we can do this like reversing of the answer, suppose we should have flipped 1, but we didn't. So suppose we should have flipped the card with 1 on it, but then we'll handle that by considering taking the complement, because that will, if we put 1 at the beginning but we should have put 1 at the end, then doing this check will take that into account. So really we can assume that like without loss of generality, we put 1 at the beginning. Note that whatever solution is determined from putting 1 at the beginning, we could again take its complement, which would then be determined by like putting 1 at the end. And so if we put 1 at the beginning, then like the solution we get will be determined by whether we flip 1 or not. And every flip in the future will be like determined by this 1 flip. So it means that like this would cover that. That's the intuitive, I guess, idea. So I don't know, maybe. But what that means is that we can do whatever we want with 1. So let's assume we put 1 at the beginning of the array that has to be sorted. So then whatever other number we get, say this is, for example, like 7. Actually, no, this is 9 in this case. That has to be on the other side. So now, look at this number. This is a number. Wow, it's a number. Right, so when we have this number, we have possibly some numbers that are greater than 9. So for example, what do we do with 10? Well, 10 can never be on this side, right? Because we just put the 9 down, meaning that everything greater than 9 cannot be, because we put this at the beginning of the array, everything greater than 9 can't be on this side because it's greater than 9, so the array will be reverse sorted. So now basically, when we put this 9 down, we force everything greater than 9 to be on this side of the array now. So now we assume we're going to put down everything greater than 9. So let's simulate doing that. Right, so we have to put down the 10 now on this end, possibly making some flips if that's necessary. So now, look at the values we put down. So initially, let me make this diagram. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So when we do this, we put down this value and we've put down this value. So now we put down 10 and 3. We put down 10 and 3. Meaning that now we put down 10 and we put down 3. Cool, so what does that mean? Well, when we do such a thing, now we put down the suffix containing 9 and everything greater than or equal to 9. Meaning that like we've sort of handled the large values. Every other value we're going to put down will be smaller than these values. Meaning that like we can kind of ignore this, because we know everything will be smaller than this. So everything we put on the right will be smaller than this 10, and everything we put on the left will be smaller than this 9. So they're kind of irrelevant. And similarly, when we had that before, we had the same situation with 1. 1 is the smallest. Everything we'll ever put down afterwards will be larger than 1. So we can sort of get rid of that, right? So now when we put down everything that's greater than 9, we assume 9 and 10 are handled. So what that means is that now, well, we still have this 2. And again, because we have this 3 here, everything here must be greater than 3. Yeah, everything must be greater than 3. That makes sense. So what that means is that this 2 is forced to be on this end. So if at any point like this forcing doesn't work out, then we're sort of screwed. It means there's no answer because, again, these moves are forced. We have to do this because otherwise it's not possible. There's nothing else we can do. So really, now we have this being forced. So we have 2 and whatever paired with 2. So that's 7. So now, once again, we have this 8 being forced to be put down on this end. So this 8 will be put down with this 5. And then now this 4 can't be here, so once again it's forced to be here. And now we have an answer. And so the thing we got is the number of flips that it took us to get here, right? And again, we can always take the complement. So in this case, we put down 1, 9, we put down 2, 7, we put down 4, 6, but we had to flip these. We put down 8, 5, but we had to flip that as well. And we put down 10, 3, which we had to flip as well. Meaning that this took 3 flips. But instead of doing that, we could have instead only flipped these, not flipped any of these, and then put the whole array in reverse. Meaning that instead we can use 5 minus 3 flips, because we flip everything except for these 3, meaning that we use 2 flips. So at any point, if this sort of like forcingness doesn't work out, then basically there's nothing we can do. So yeah. Let me try and construct a case that makes a bit more sense. So it takes a few more cases to understand the rest of the solution. Have we finished system testing? We have finished. Okay, I'll check my delta after this, I guess. I doubt it's positive, but who knows? I'm assuming people didn't fail system test that much. Yeah, I doubt it's positive. Alright, that's disappointing though. Just because of this stupid penalty. Could have done so much better. Alright, so let's take the case 1, 6. No. 1, 4, 2, 6, 3, 5. Is that how that works? Or is it 3, 6? Wait, what? Wait, will that work? I feel like it doesn't. 1. Okay, yeah, that does work. So we consider the same thing. So we have to put 1 down somewhere. Let's assume we put it at the beginning. Then we have to put 2 down somewhere. Actually, no. The way this works is now the 6 is forced to be on the other side because we already put down a value smaller than it. Meaning that now we're going to put down 6 on this end, and then we're going to put the 2 there. So now we've used that. So now this 3 is forced to be put down on this end, and the 5 is forced. Actually, no, the 3 isn't forced, but the 5 is forced. So the 5 now has to be here. So when we have multiple forced values, like in this case, what we do is we always consider the largest one first. Because like, suppose we didn't, if we put down the 5 in this forced position before we put down the 6, then we're automatically going to have like something that isn't sorted. So let's not do that. We consider the largest forced value at any point. So really we're like sweeping 2 pointers across, and if any value is never forced, then like we're good. Cool. One final thing to consider is that this doesn't always apply to the whole array, the taking x and then possibly taking the complement of it. Sometimes we have like independent subproblems, right? So like, for example, say we have 1, 4, and then 2, 3. So when we put down 1 and 4, 1, 2, 3, and 4. So we've used 1 and 4, right? So like, this is the smallest possible value. This is the largest possible value. So nothing is forced. Even though we put these cards down, nothing is forced. Right? So this is always going to be less than anything we could ever put in this array. And this is always going to be greater than anything we can ever put in this array. I mean that like, once we put this down, we can sort of ignore it. I mean that we can solve this. We can solve the values 1 to 4 however we want. And then we can solve the values 2 to 3 independently. I mean that if we consider the problem solving 1 to 4 and then solving 2 to 3 as different problems because they're independent of each other, the answer we get from taking this or taking its complement is also independent. Meaning that if this takes 0 flips, then this would independently be the minimum of 0 and 1 minus 0. And this would also, say this took 1, this would independently be the minimum of 1 and 1 minus 1. Then we add these together. So for more complicated problems, for example, we would have to consider these minimums independently. So for example, I made this case for n equals 10. You can copy it if you want. I don't know. I mean, I made this case for n equals 10. And basically, it's like, it's the sample, but like for the first 5 values and then the last 5 values, it's the sample. So basically, like for the sample, everything greater than 5, I added 10 to it. And then we recreate the sample again in here, noting that it's independent because we can solve the sample independently and then have all these values. Like once we're done with these, nothing will be forced. So we solved that problem. Now we solve this problem independently because it doesn't matter. So then I just added +5 to everything in the sample here. So it's the sample twice, where the sample is sort of contained within the sample. And so what that means is that this is going to be the values 1 to 5. This is going to be the values 16 to 20. They're going to match with each other. Then we're going to have the independent problem of 6 to 15. And this is also like, I flipped everything on this side of the sample, I think. Or no. Was it the inner ones? Yeah, I flipped everything on this side of the sample. So what that means is, independently, this would cost 2, and this would cost 3, meaning that in total it would cost 5. So if you only considered the total thing, so the minimum of 5 and 10 minus 5, you would get 5 as your answer. But because these are independent problems, we can consider this quantity independently, meaning that we can solve each of these independent problems with 2 operations only. So in total, we can get an answer of 4. So you can check with that case, or you can make your own, or just check things. But yeah, that's the idea. That basically settles it. Yeah, I think you can also make a minimum break case of size 6 or something, but it doesn't really matter that much. The point is, like, you have to consider every problem independently and solve them independently. Okay, let's see how we did. I'm scared to see this. It's such a bad penalty. It's like sad. 1/32. Okay, that's actually better than I had before. Oh my god. Oh my god. Wow, he had even worse penalty than I did. Jesus. I assume it's like a very small negative or something. Oh god. My friends have not done the greatest. Jeez. That is not a nice score. Did you try E? Did you get it? Okay, well, for some reason rating changes aren't showing up. Maybe I should get carrot or something. So, yeah, that's solutions. And that's it. I hope you enjoyed. I have absolutely no attempts on E or F, so that basically, that's that. Like, I barely read it. I just laughed at the statement for E and then closed it because I didn't have that much time left. And then F is like a thing, so we sort of have this like flip and balance stuff, and we also have bracket sequences. So like where it's like the corresponding like flip is like flip them or something, and then balance is like bracket sequences or something, which is kind of cool. Anyway, minus 16. Okay, that's sad. Everyone else is getting positive delta. All right, well, I guess that's how it is. All right, goodbye.